Welcome to The Plunge, a cryo-EM podcast from Mimi, Mike, and Liz, sponsored by Thermo Fisher Scientific.
Welcome to another episode of The Plunge. We're really excited to be here. I am Mimi Ho from Columbia University. My co-hosts are Liz Kellogg from Cornell and Mike Gianfrocco from University of Michigan, Ann Arbor. And our guest for this session is Mark Herzik from UCSD.
Welcome, Mark. So we're excited to have you here. You've been a pioneer in cryo-EM, pushing the limits. One thing that jumps to mind for me personally was the work you did with Autolase, with Mengyu and Gabe. And it felt like the field we had these sort of blinders on, and we didn't know what we could do, and we all had these arbitrary limits of scopes and molecular weights, and you helped us push it through with Autolase. So do you want to tell us about how you got there and how you pushed through this hurdle that everybody faced?
Yeah, for sure. That was a lot of serendipity, honestly. We had just gotten the Arctica and we were benchmarking it. We were trying to figure out what it could do, and quickly we put on 20S proteasome. Everyone was using 20S proteasome that, honestly, we got donated from Yifan Cheng's group, which was great. Went sub 3 angstroms really quick, and then we were like, okay, let's start screening samples. And so we put on one of our samples, and very quickly it went to things like 2.5, 3 angstroms or something. One day it was like right around 220 kilodaltons. Can we go smaller? Can we go less than 200? And so then we were starting to find samples. What can we use to benchmark? What can we find? And so I went to the PDB and I was like, sub 200, something I can purchase that we can put on the grids. And then I found Autolase in the high molecular weight standards box that you get from GE. Mm-hmm.
And you didn't go down the alphabet and just go Autolase.
Right? It was just, I created a laundry list right on an Excel spreadsheet, and Gabe and Mingyu and I sat down. And it was Autolase, let's look for that. And it was literally in the deli case, just right across the lab.
Nice.
And so we put it over gel filtration, we put it on grids, and we saw Autolase, and it looked great. And then we started collecting data. And then we started noticing that when you got to really, really thin ice, they were popping every single time. And we couldn't figure out why. And then we got into a really good set of squares where all the images had tons of Autolase particles all the way across. And the images looked great. And then we went to another square, and then all of a sudden, boom, they're popping again. And we realized that when you had more diffuse Autolase, your ice was thicker, and it just wasn't behaving properly. And so that's when we really started looking okay, we have to crowd Autolase because that's when the ice is the thinnest it can possibly be. And so then we went back, and Mingyu and I were just blotting until our eyes bled until we got this super thin ice with Autolase wall to wall to wall, and then it worked beautifully. So
yeah, I didn't actually know the backstory of that. That's really fascinating. That you, and also a little bit counterintuitive that you would have to crowd it so much, because I remember, right? I mean, it used to be everybody was concerned about their particles being too crowded, right?
Yes, exactly. And I remember when we first showed the images I first showed the structure in group meeting. And it was 2.6 angstroms, beautiful density. And then I was and then here's the micrograph. And I remember all of the established electron microscopists being nope, you can't do that.
Yeah.
They're too close to each other.
Exactly.
And it worked. It just somehow clicked and worked with the algorithms and stuff that we have. And so now we're seeing it more and more. It's you really got to push them to the thinnest ice. And when you do that, oftentimes they get, kind of this wall-to-wall type density.
So I think one thing that I think about is, I think it was the next paper on alcohol dehydrogenase that you guys did. That data set is impressively dense. Almost you look at it and you're I've tried to help people in my lab analyze it, and we've looked at it and we're I don't know how Mark analyzed this data set.
Yeah, so that was a similar thing where Mingyu and I were freezing grids. We were going back and we were screening different grids, different concentrations and stuff. And we had a screening, I think it was a Talos 200 we were using. And we put the grid in there, and we took a low res image, a whole mag image, and we thought it was all empty ice. And we're oh, we can't figure this out. And then we looked at the Fourier transform, and you could see like almost like a pseudo lattice.
Wow.
And I was like, there's particles in there. And so sure enough, Mingyu took a high-res image, and you could see just wall-to-wall aldolase.
Wow.
I mean, alcohol dehydrogenase. And it was, and so that's what we went for every single time. So.
Yeah, it's super impressive.
So do you have any advice for trainees in how to challenge paradigms while also approaching it sensibly and logically?
Yeah, that's a great question. I think early on when I was learning cryo-EM and being in Gabe's lab, the benefit we had was like we had Legend on Appian, right? And so what I ended up doing was, okay, this is the final particle stack that came out. Let's work our way back and figure out what worked, what didn't work. And it was just this agnostic approach. It was like, I don't really care what worked per se. Just tell me what worked so I can apply it to other stuff. And we ended up finding it was like, you got to shoot the center of the holes, because if you shoot to the edge, the ice is thicker. You got to push the particle density so you can get even thinner ice. You got to blot longer. You really need to make sure that you're monitoring these things. If you see, a lot of thick ice in your images, they may go to like, semi-high res, but they're not going to really push the high res stuff. And then, one of the good examples is in one of our papers, we started to classify our particles. And we were getting two classes, and we had no idea the difference. They looked isostructural, but they were clustering based on like difference to focus estimates. And what we found was like, okay, all the high res particles are 1.5 microns or better. Everything else is getting lumped into this other class that looks the same, but it's just lower resolution. So then it was like, okay, let's crank until we get as close to focus as we possibly can. Once you do that, you need really thin ice. And it all comes back into play. It's like, let's make sure that we can collect at 1 micron to focus. If you can't, your ice is probably too thick. And it's literally just like, where's the good data coming from? Why is it there and where is it there? And then just latching onto something. Okay, let's test it.
Yeah, I really like that. Like data-driven approaches that are not biased by preconceived notions.
Exactly.
Right?
And I think I felt like this basically was born out of a collaboration that I had in Gabe's lab, because we had this one complex that once it came off of gel filtration, we had like maybe 20 hours, 24 hours or so before the complex was completely dead. And it was a week-long prep. And I was like, I don't want to waste this specimen. I don't want to waste this person's time. Let me make sure I'm doing the absolute best to make these beautiful grids. And it was like the freezing conditions, how I was handling the grids, collecting the data, and all that. So
one of the key things to the aldolase work and all of that optimization that you just told us about is getting really, really, really thin ice to the point where you can image even at like really, really close to focus, right? And so what was the key to allowing you to be able to do that?
Yeah, I think there's a lot of variables that go into it, but I think also Mingyu and I and Gabe, we were always champions of the manual plunger, right? And I think it was a mixture of just it being so much quicker for us to freeze and screen, because we could freeze a grid really quickly, screen it, go right back, freeze it, tune the conditions just a little bit, and that interplay was great. And then what we found is like, because of the mechanics of the manual plunger, like you're blotting the grid and it's perfectly parallel. You're making good contact across the entire grid surface. If you get that one good grid with the great ice, that whole grid is almost usable, right? And you can start screening and doing stuff. And so ever since then, that's what we've done. I teach my lab how to manually freeze grids. I haven't used a robot in, I'd say probably 7-8 years maybe or so.
Yeah. Do you have any tips?
Tips: don't drink coffee.
Yeah. No, that's definitely.
Yeah, that's the one thing that I've noticed is once you contact that grid, your hands have to be as stable as possible. If you have any rotations or translations of the blotting paper, you're going to start ripping the foil off, or worse sometimes is you break that liquid contact layer and you get big pockets of like thick ice. And so it's literally just like committing to the blotting and then holding it steady and then releasing and doing the motion. And so I think, a lot of people, the analogy I make when I teach people is like watch pitchers in baseball, right? They have a very detailed mechanic on like, once they get ready to pitch, they do everything the exact same way, except how they hold the ball and release the ball. you're doing the exact same thing. Make sure you're comfortable. Make sure your hands are steady. Make sure you have the blotting paper exactly how you want it. Make sure your grid's exactly how you want it. And it should just be muscle memory at that point.
How many tries does it usually take your students to pick it up?
It varies a lot. Sometimes I've had one student who got it within like the first screening session. Wow. And I couldn't believe it. And I've had a few people, it takes a few dozen screening sessions until they really get the mechanics down. And I have a few people who it works for one specimen and then they change specimens, it doesn't work as well. So then they start fine tuning, blotting time or mechanics or whatever they need to do. I have one student, one postdoc, who actually, he turns a metronome on when he starts freezing. And so he times the blotting to the actual metronome. And so that's how he internally...
Oh, that's clever.
That's so
exactly.
cool. Yeah.
And so he times everything based on that metronome versus your internal counting.
Yeah,
So
that's a really good idea.
That is a super good idea. So we've started doing manual plunging in our lab. I didn't use a manual plunger as a PhD student, but in our lab, because we're doing cell work now and we're freezing cells, so we're doing it on manual plunger. And ours is broken.
yeah.
So there's a little
often
spring
are,
in
yeah.
it that is worn out. And so did you build your own manual plunger? Did you go purchase it from somewhere? Where did you get the design? Do you have a design shop do it?
I basically took the version that they had at Scripps that I learned on. And there's one random person up in New York who was building it. And so I bought one from him, and I was using that for a little while. And then the dewar broke. And so I was like, okay, I got to replace the dewar. And so I built a little dewar that I 3D printed. And then the cable broke. I was like, okay, I got to fix that. Here's another piece I have to remanufacture. And then I started talking to people, and they were like, okay, what plunger are you using? And I'm like, this one design, this one random person builds it. And then every conversation was going the same way. It was like, yes, we would like a manual plunger, but there's always this one random person in some state who's producing it. They're different, there's no warranty, there's no nothing. And so then I decided, why can't we just make it to where you don't rely on this one random person? So now what we're doing is we're making one that it's completely 3D printed. The entire thing, top to bottom, except for the ring stand and the dewar. And the idea is you can basically get the design and you can 3D print it. It's maybe a few $100 at most. You can customize it. You can do whatever you want. And you don't rely on one random person. All you need is the files and a 3D printer, or potentially even buying it at some point from a bigger vendor. But hopefully we can get more of these manual plungers in hands across the U.S. and the globe. So
Yeah, that actually really brings up an important point about having access to resources in order to do cryo-EM.
Yeah, exactly. And I think, fundamentally, I hate the idea that you have to be at an elite top tier institution to do something as convenient and as powerful as cryo-EM, right? And so, breaking down all those barriers, like using cheaper microscopes, cheaper plungers, doing data collection better, faster, using, less powerful clusters, so to speak. And so just basically chipping away at all those hurdles that prevent people from being able to do something that would greatly answer whatever biological question they have. And I think for me, being able to build a manual plunger that gets everybody access to start at least preparing grids, using these national centers to collect their data, I think that's a big first step, hopefully.
Yeah, that's really powerful.
Yeah, I feel like a lot of us who come from big labs that are well funded don't even think about that kind of thing at all, right? And then we start when you start this job, you start serving on sections, or you talk to people, and then you learn a lot about kind of the challenges of being in a smaller place that isn't as well funded and doesn't have access to these things.
Right.
Is that something that you, I think, have been thinking about for a long time, or is it something that you also just encountered when you started your own lab?
I think it's a little bit of both, honestly. I think it really hit home when I started my own research group and I was looking at the budgets and how much money was being tossed at cryo-EM. But I think even before that, I think it's part of my growing up, right? I think some people know this, some people don't, but I'm a first-gen college student, right? And I think having come from a family where I had what I needed to survive, but I didn't have a lot of like these affluent amenities that people typically have, right? And so, I had a job all the way through high school and college. I was, we had things that were on layaway, and we were really concerned about budgeting because my dad was the only one that worked. My mom was a live-at-home mom, and it was great. They did everything they could for the kids, but you were really cognizant of like, yes, I would love to have some Oreos, but it's probably not in the budget, right? Yeah. And so that kind of carried over into, how to do science as well. It's like, yes, you could probably use a lattice light sheet to collect all your beautiful data, right? But it's really expensive, and you probably shouldn't do it depending on the question that you're going after, right? And so it's a mixture of using the resources you have, but making sure you're very conscious of just not throwing money at everything, right?
So hearing you talk about this, another question that kind of comes to my mind is not only are you having to overcome the challenges of going to college, being the first in from your family to go to college and succeeding there, but also that's another hurdle to overcome in your PhD. So, can you elaborate, like what were some of the barriers that you had to overcome being the first in your family to go to college and also the first to go to academia?
I think a lot of it was just finding the right either friend group or a champion. Like I always found a champion at each stage, right? It was like, in high school, I wasn't supposed to go to college. Like I was supposed to go into the family business doing like construction repair stuff. And I had a friend who was taking the SATs and the PSATs and all of that. And so by proxy, I was like, I should probably look into this. And then he was guiding me on like, yes, you should do this. Here's a prep book, do this. And then I got into college and I was like, oh, great. Now I can move into this next step of like going into science and doing things. I got into college and I had a grad student TA in one of my science classes who came to me and was like, you've got great hands. You got great lab hands. Would you want to come work with me? Mm-hmm. I was like, absolutely. I didn't even know how to get into that arena. And sure enough, I went and worked with him. And then he was like, if you're interested in going to grad school, let's talk about stuff. And then he was my champion. His name was Mehmet Sen. He was a grad student at U of H. And he laid out like, you should think about these things. Think about schools. Think about what type of lab you would want to be in. Mm-hmm. And then I started applying to grad programs. And then, I went from University of Houston to UC Berkeley, and somehow I got in. But like literally, that was the first time I ever got on an airplane, right? And so there was all kinds of stuff. How do I interview? How do I talk to people? What should I talk about? Mm-hmm. How do I even approach this? Mm-hmm. And then I got into Berkeley, and then I found another champion of our friend circle in the grad class. And they were like, think about these things. This is what we're thinking about as far as mentors. And then postdoc, it was the same thing. And now in faculty, I have a faculty mentor, Kevin Corbett, who like, he's my champion. Like I text him all the time. This is what I'm dealing with as far as mentorship. This is what I'm dealing with as far as grant stuff. What do you recommend? And having that great resource is what keeps everything moving.
That's a really great point. I really like that answer.
Yeah.
Especially because I feel like it's just not just about having the mentors, but the community.
Yeah.
Right? And I usually like to not only look for mentors ahead of me in my career path, but also peers that I can rely on as mentors, like peer mentoring.
Mm-hmm.
So
Exactly. And I think, being a first-gen student, you don't really know that you're a first-gen student without actually talking about having a networking circle, because it's not something that comes out in common conversation. But like having a network of other first-gens, you realize like there's a lot of little barriers that you have to go through. And if you don't have a champion to help you out with that, you might get stuck in something. And so it's good, especially at UCSD, because we do have a big network of first-gens. We have also the Preuss School, which is right next to UCSD and affiliated, who helps kids go through high school who are potentially the first gen of their family. And there's a lot of great resources in that as well.
Yeah, I feel like that was one of the things for me when going to UC Berkeley also and being a TA. I felt being at a big public university and helping people learn, and they're sort of learning. You can actively see them coming in, either they're transferring from a community college or they're you can see what's happening and how they're learning and sort of going beyond where their family was before. And I feel like that's also why I like working at University of Michigan also, where it's like a big public university. I just like that philosophy.
Exactly. And that's one of the reasons why I chose UCSD, is because it's a big primary undergraduate institute who have a lot of diverse background students. And the class I teach is one of the first transfer classes you get from like a community college into like the biochemistry major. And so the first lecture, I always tell people, like, I'm a first gen, this is what I've done, reach out to me. And a lot of people come in, they're like, we have no idea how to actually operate at this big university level. And so then they get into a network with other kids who are in the same, type of situation. And you build this network of people who can help each other, whether they realize it or not. So
That was a perfect answer.
Yeah. I was kind of curious. So you talked about like having a champion at every stage. Is that something that you knew to seek out, or like was it luck? I mean, was it a little bit of both?
it was a little bit of both, honestly. Like, I think growing up and moving forward now, like, I always try to find someone that I can rely on. And so, like, when I was an undergrad, not even really looking for undergraduate research per se, my grad mentor, he found me, so to speak. And then, like, my relationship with Kevin, that just was born out of natural conversation. Like, we kept seeing each other at seminars. We kept seeing each other across campus. We saw each other because we were doing cryo-EM. And I kept asking him more and more questions about things. And I finally asked him, I'm like, dude, you're helping me out so much. Would you be my faculty mentor? And he's like, absolutely. And so that just was born out of just a conversation, effectively.
So Mark, there's a really amazing paper that came online from your lab. It's in first release in Science. Do you want to tell us about it? It's really impressive on many fronts, but I'll let you tell us about it.
Yeah, thank you. It's a collaborative project between my group and that of Akif Tejan at UCSD. So his group, they're experts in nitrogenase biology and mechanism. So nitrogenase is the only biological enzyme that we know that can convert, nitrogen into a functional form of ammonia, right? Super relevant as far as just general biology in general. But what was nice is it was an enzyme that had been studied by X-ray crystallography for decades. And everything that they knew about it as far as like assembly, all these things were all static snapshots. And the enzyme, it catalyzes this very complicated mechanism. And so I was judging a poster session where one of his undergrads was talking about making mutants in the native source to purify nitrogenase. And his grad student jumped in, who was mentoring the undergrad. Her name's Hannah Rutledge, the first author on the paper. And she's like, you're a cryo-EM guy. Can we do cryo-EM of this? And I'm like, we can do cryo-EM of almost anything. Let's try it. And so we started looking at it in grids, and then boom, COVID happened. And so it then quickly turned into just me and her trying to look at samples and try and do things. And we got a pretty high-res structure shortly after pursuing the project. And then we started doing some mixing experiments, looking at how we can assemble the full thing. And we got some nice images. And then she came and she's like, this is looking good. Can we do it under turnover? And I was like, that's kind of what we want to do with cryo-EM moving forward. Let's try it. And after months of optimization, we finally got the conditions dialed in, where we have everything undergoing ATP turnover conditions with nitrogen as the source, and then got some nice images. Everything was looking good. And I was like, don't pull that sample off the microscope until we have 20,000 movies. And we collected for almost a week straight until we had all the data we did. And we ended up getting 20 million particles, sorting out different states and breaking all aspects of my cluster and breaking nodes and disk systems and all kinds of stuff. But yeah, it was a tour de force. It was a grad student in Keith's lab. It was a postdoc, Brian Cook, in my lab. It was a grad student, Hong Nguyen, in my group, and we all just, went at it. And so it's great. It's a lot of work, but I think it's exciting to actually see this thing under turnover conditions in EM images.
Yeah, it's amazing.
Yeah, that's amazing.
That whole process is the future, like you said, and just amazing to see, and then all the structures that you had, and the resolution as well, because the resolution you got was two angstroms, below 2.
Yeah, the lowest res one we got was 2.5 angstroms.
Yeah,
and so
impressive.
It's a mixture of, it's purified from the native source, and so it's well behaved. The grad student's been working on this for 5-6 years, and so she knew the system really, really well. And then we were just trying to squeeze all the data we could out of the images we had. And so it just all came together. It was like the perfect storm, basically.
Well, congratulations. That's
Thank
really
you.
cool.
Yeah, it's
really
great.
cool.
It's exciting.
Thank you so much for coming and hanging out with us today. This is really nice.
Yeah, thank you. This is great. I love the name, by the way. The Plunge.
Yay. Good job, Mark. Yeah.
Thanks for listening to The Plunge, a cryo-EM podcast from Mimi, Mike, and Liz, sponsored by Thermo Fisher Scientific.